your head. And our goal, because we're computational vision people, is to think a little bit about how to get the computer to manufacture some of that information.
Can you find some interesting examples of impoverished motion from the web? Now, these don't have to be videos of dots moving. They can be anything where you have very little to go by, and yet your brain reconstructs and interprets the overall motion, sometimes correctly, sometimes not. You can paste in links to web pages, videos, or papers. Now here's an old video from Cornell University. It shows how the same motion can be perceived differently in different scenarios. Fascinating, isn't it? There is a lot more in this video, linked below. Feel free to discuss this and other examples you found on the forum.
Another example here, mosaicing. Now, we've talked about mosaicing before. We talked about panoramas, about aligning images and bringing them together. Well, instead of just a small, discrete set of images, suppose you actually have a video, so you're taking your camera and you're panning it around. What you might want to do is make a single image, okay? And this comes from Michal Arani's work, of where you can see where all the frames are. Okay, you can sort of see this jagged line, each one being the edge of a frame, and you realize what happened is the camera was swept out this way, all right, and I'm able to make this single image, all right? And if I'm rotating my camera about its axis, I'm not actually doing any translating, the reconstruction can be perfect because I don't have any motion parallax. And if these things are planes, I have to align some points. How many points does it take? It's a homography question. That's right. Even Megan got 4 points for that. And in fact, if I am moving but things are really on a plane, it's still 4 points. So there are other applications of motion analysis, segmenting objects in space-time. Sometimes you can get the three-dimensional structure. If you know how the points are moving, you know which point is which, just like when you saw the person. You might want to learn the dynamics of how something's moved. Maybe you're doing physiology, and you're watching people moving, and you want to understand something about their gait and the dynamics of their gait. All right? Recognizing events and activities. You'd like to be able to say, what just happened in the video? So it's not just object recognition, it's action recognition. And finally, you might just want to process the video and understand the motion to improve the quality. So you might do motion stabilization, right, so that you've got this jerky camera and you'd like to get a nice smooth video out. There are simple ways of doing that and complicated ways. In fact, a colleague of mine here, Irfan Issa, and a former student of mine, Vera Quatra, and some others did some work on stabilizing video, especially when you have rolling shutters and cell phones. Anyway, these are all reasons for wanting to process motion. So for the remainder of this lesson, and then the next one, and then the next one, and the next one too, we're going to be talking about motion estimation. Basically, given a sequence, tell me what moved, tell me how it moved. Generally, you can say there are two different approaches to this. The first approach involves feature-based methods. Now, feature-based methods are just what you might think. Extract some visual features like corners, textured areas. Oh yeah, we know all about that. And track them across multiple frames. So that is, find them from one frame into another. Oh, we know all about that too. And that will give you what's called a sparse motion field. That is, you don't have the motion of all the points. You have a motion of a bunch of points that were good to track. All right? But that works really well when image motion is large, so you move like tens of pixels, and you have a significant change between frames. The other method, class of methods, are what are called direct or dense methods. In dense methods, you're sort of directly recovering the motion of every pixel, of each pixel, from the fancy word is spatial temporal image brightness variation. So in other words, remember that volume, x, y, and t? So you can think of gradients, you can think of flow within that volume. And what you're trying to do is you're trying to recover that flow based upon how the appearance changes over time. It gives you a very dense motion field, but it can be sensitive to appearance changes. This type of analysis is suitable for video, where you're getting samples very quickly, so things don't move very much in time. And in fact, if things are somewhat smooth in time and space, I could say, well, from one frame to the next, I can talk about how things are moving, like, say, a first derivative. If you're worried that a Taylor series expansion is in our future today, well, maybe tomorrow, yes. Okay, but the idea is that it's good for nice, dense, smoothly moving things. We've already talked a lot about finding features, detecting them, describing them, and matching them. And so we're not going to do much more in terms of that feature matching for motion. Okay? Instead, what we're going to be doing over the next couple of times is focusing on the dense methods, where we look at the derivatives, we look at how things change. And just to sort of spill the beans all the way at the end, the best methods currently use a combination of the feature to get the long-range matches and local gradients in order to get the dense, shorter range. So you already know about the feature stuff, so now we need to go over the dense, direct stuff. And that's what we're going to be doing over the next couple of lessons. All right, welcome back to computer vision. Last time we introduced the notion of image motion. We said how motion is actually a construct of your head, because there's just a bunch of static frames, and your mind, your brain induces this notion of believing that there's actual motion. So the question then becomes, how do we compute that motion? And we talked about motion estimation techniques are going to be the methods of doing this. The first one that we mentioned was feature-based methods, where you detect, describe, and locate features in your subsequent frames. And we've done a bunch of that in looking at how we do the SIFT stuff and panoramas and those kinds of things. But the other methods were called direct or dense methods. And that's what we're going to be focusing on today. Direct and dense methods, what they do is they recover motion at every pixel in the image, and that gives you a dense flow field, and it's based upon what we call the spatial temporal brightness variations, how the appearance is moving and it's changing. It can be sensitive to appearance changes, but as long as you're getting sort of video-like sequences where you have frames sampled regularly and frequently, it works pretty well. The first thing we have to do is define what's called optical flow or optic flow, because what we're going to be recovering today is the optic flow. And the optic flow is the apparent motion of objects or surfaces or pixels. And the reason I say apparent will be clear. Here what we have is a Rubik's Cube looking device, although here it's black and white, so it's just a denuded Rubik's Cube. And it's been placed on a turntable that's been rotating around this way. If you take a look at these little patterns on the side, you can see what the rotation is. I'm pretty sure this was done by Rick Soliski, because he looked at these gray codes to do the rotation. Now, what's a little bit hard to see is that over here are these little arrows that are showing you the motion. And of course, the motion is greater in the front of the turntable than, say, on the cube, because it's closer to you and it's rotating a further distance. But you'll notice that there are no arrows up here, right, on the white part of the turntable. Now, it's moving exactly the same way as the part of the turntable that has the markings on it, but you can't see it. There's no apparent motion because there's no contrast, there's no texture, there's no indication that the pattern is moving. So optic flow is recovering the apparent motion of objects or points or surfaces. The actual motion, by the way, is sometimes called the motion field. We're not going to talk about that today. We'll talk about that not next time, but time after a little bit, but what the underlying physical motion is. Today we're talking about motion in the image. So let's take a look at a sort of very simple definition of the problem of optical flow or optic flow. So here I have 4 points, conveniently color-coded so you can tell their difference. And this is their location, x, y, at some time t. But they're all going to move, okay? So they're all going to move in some direction such that at t plus 1, they're at a different location. And that's drawn here. So the points moved in the direction of the arrow. You don't actually get to see them doing the movement between t and t plus 1 because we only get samples at t and t plus 1, but that's just showing you how they move. And in some sense, our goal is to actually recover those arrows. So the question we want to ask is, how do we estimate pixel motion from image I xy of t to image I of xy t plus 1? We're trying to estimate that motion. So What we have to do in order to estimate this pixel motion is essentially solve a different kind of correspondence problem than we had from stereo. It's kind of sort of related, but it's somewhat different here because the pixels can move however they want. Given some pixel in I, X, Y, T, so here's one, here's one, here's one, here's one, look for nearby pixels of the same color in X, Y, T plus 1. Solving this problem is what's referred to as the optic flow problem or optical flow problem. And in particular, we're going to have to look at two words. One is this notion of nearby, and we have to look at what we mean by the same color. What we want to do is we want to look at these terms nearby and same color a little more carefully. So we have two key assumptions, this notion of the same color and nearby. The same color is referred to here as color constancy. And basically this says that a point at x, y, t, if we knew how it moved to some point x prime, y prime at t plus 1, that point will be the same color. Okay? So, and if this is a monochrome image, grayscale image, then that point will be the same brightness. Okay? And that's the color constancy or brightness constancy. All right? And then the second thing is that we're going to assume that these points don't move very far from one time to the next time, from t to t plus 1. And if you think that's because we're going to do something in the Taylor universe, you're absolutely right. So let's look at these equations a little more carefully. So the brightness constancy equation. What we're going to do is assume we know that some pixel is moving an amount uv. U is the amount in x, v is the amount of y, when we get to t plus 1. Okay? The brightness constant constraint equation can be written like this. I of xyt, that is the image at time t at location xy, brightness if it's grayscale, color if it's color, is going to be the same at t plus 1 at location x plus u, y plus v, where u and v are the amount the point has moved in the x direction and the y direction respectively. So that's called the brightness constancy constraint, and in fact I can rewrite it like this. 0 is equal to the x plus u, y plus v, t plus 1 image minus the original I of xyt. All right, that's the brightness constancy constraint. The second assumption was that we get a very small amount of motion. Okay? So that basically u and v, let's assume they're like 1 pixel or part of a pixel, or just things are changing smoothly. Yes, you know what's coming. What that means is I can estimate, using the Taylor expansion here, that the value of an image displaced from x by u and displaced from y by v is approximately, well, it's exactly here by order terms, it's the original value plus the gradient x times delta x plus the gradient y times delta y, u and v are delta x and delta y respectively, plus some high order terms. Right? Remember Taylor expansion, if you go infinite series, you get the exact solution, but we're just going to say plus some high order terms, and then when we make those high order terms go away, poof, wow, isn't that great? I've got the power right here. All right? Then we say that it's an approximation, okay? So we say that x plus u, y plus v is approximately the original image plus the gradient in x times delta x plus the gradient in y times delta y, or v. Okay, so now I've got these two equations. I can combine them. The first one is obvious. This is the original brightness constancy equation. The second one, after I substitute in the Taylor series expansion, there's a little sleight of hand going on. What I'm doing is I'm substituting for this value. Remember, it says that I can get the location at x plus u, y plus v. All right? I can do the Taylor expansion. So here's the original xy at t plus 1. And then there is this derivative part, okay? I of x times u, I sub y times v. And I of x is the derivative in the x direction. I of v is the derivative in the y direction. Now, students will usually ask me, wait a minute, is that a time t or a t plus 1?
Is that a time t or a t plus 1?
The short answer, doesn't matter. The idea is we're going to assume that things are changing so slowly and so gently that the derivative at a particular point is going to be the same whether I look at t or t plus 1. It's a little bit, shall we say, dicey, But actually, in the limit, it's true, and we only care in some sense about the limit. So taking those two equations, I've now rearranged things. I just moved this part over to here,